Welcome to the current episode of iReveal, which is going to be the first episode of 2024. So we managed to do like a whole year of iReveal, which is exciting and which was actually pretty easy because we started pretty late in last year, but nevertheless. Okay, so let's get straight down to business. If you might be remembering after the New Year black hole, what we ended up last year with was discussing consensus algorithm. And algorithm like from the mathematical perspective, like how can we like actually prove that what happens should happen, how we can ensure safety, how we can ensure liveness, and all that. Well, actually, didn't like really went into too much detail about like how like exactly things work and like into formal proofs, but hopefully I was able to give you some intuition about how consensus works by building like working consensus algorithm starting from scratch by just basically inventing some stupid algorithm, realizing why it doesn't work, and like patching it to overcome each particular problem until we ended up with something which actually works. And to highlight the important point is that what does it mean that consensus algorithm works? As FLP impossibility result teaches us, this doesn't necessarily mean that the algorithm reaches consensus no matter what. It's for every consensus algorithm, there could be particularly nasty scenario with a network connectivity when although like some message sometime gets passed through and eventually every message gets delivered, no decision is being made at all. So kind of like it's possible for every consensus algorithm to get stuck even in a relatively connected network, as long as we allow one process failure. So kind of like the game of consensus is to maximize availability, to figure out how to make decision happen using as few nodes, as small amount of network connectivity as possible. Okay. What we are going to discuss today is how can we practically implement consensus to drive a real system. So if the last lecture was mathematics, today's lecture is about pragmatics. And it goes back to the lecture we had before that, about replicated state machines. Okay, we don't have replicated state machines here. We only have consensus. So let me delete consensus and get back to replicated state machines. So if you recall, we said that the logical model of our let me do this. If you recall, the logical model of our system is that we have a sequence of events, kind of like they are like really sequenced in that like events happen one after the other. So let me try to do this. I'm not sure if that's the best way. So yeah, this kind of like sequence of events, and like at some points to kind of like compress the sequence and to make it finite, we actually say, okay, we are going to create a snapshot here. So we kind of like forget about all the events that happened before, like that can now be deleted. We start from a particular snapshot and we have a suffix of events built in on top of that snapshot. And that's the logical model, which relies pretty heavily on determinism. So we require that processing a specific event in a specific state always leads to a specific result. And in exchange, we get a nice model where you could do restore from backups, where you can do replace from like the historical log of events, and where there is a very nice guarantee that every change to your internal state is a single event, and a single event is bounded in size, and we love that everything in Pragmatics is bounded in size. So that's kind of that's a model that we want to realize on a distributed system. And that's why we are going to kind of like implement a pragmatic version of consensus algorithm. What we do in Pragmatics is called VSR, so view stamp replication. Although kind of like it's not exactly like pure VSR, because again, kind of like when it comes to mathematics, like there's really just one consensus algorithm. When it comes to engineering, it all comes down to like each specific implementation choice you have in your consensus algorithm. So kind of like what you have in Pragmatics is like very much inspired by the VSR, and we call it VSR. There are actually kind of like a couple of like twists on top of it, which like remixes various other advances in consensus to kind of like give what we have here. So okay, let's try to invent VSR. I lost my log. Yeah. So okay, and for now, let's actually ignore this bit about snapshots. Let's just imagine that we have a log of events, and we somehow want to replicate this log of events across multiple machines. So using ideas from consensus, well, okay, let me take a step back. So when we were discussing consensus, we really were trying to arrive at a single decision. We like trying to choose a particular value. When we talk about log replication, the problem is different. We want to decide on the sequence of events. And kind of like there's two problems like reduced to each other. But here, because we're talking pragmatics, we really start thinking about sequence of events. And in terms of source code, let's go to source code. In terms of source code, the event is a prepare message. So prepare message, as a reminder, contains an operation. So command would be prepare. That's a property of the DSR protocol. And the operation is the underlying operation in the state machine. So for our account state machine, the operation would be either a bunch of transfers or a bunch of create accounts or a bunch of lookups. We could actually, yeah, so this operation is going to be this one. Okay, so let's get back to prepare. Yeah, so prepare has an operation, and then it has a body where the body is, well, the data for this operation. So if operation is create accounts, then the body is a sequence of create accounts. Well, if operation is create accounts, and the body is a bunch of accounts which needs to be created. And here is one account. So it's just tightly packed in a single array. Okay, so coming back to this picture, like every single rectangle here is prepared, and our task is to agree on a canonical sequence of those prepares. Like what is actually the sequence of events that our cluster accepted. To make this easier for us, each prepare includes a hash chain for the parent prepare. So again, in a prepare, there is a checksum which covers the entire prepare. Well, again, let's take a step back. Let's be precise. So inside of each prepare, there is a checksum body which covers the body of the prepare, so the actual transfers. And this checksum for body is inside the header. Then there is a checksum for the header. And because the checksum of the body is inside the header, the checksum for the header includes kind of like transitively checksums over body. And then in the header, we also have parent. And parent is a checksum of the previous prepare. So actually, I think this one is drawn in like slightly less intuitive way. Okay, let me maybe try to do this from the start. Okay, so let's say that this is like the latest prepare. And this latest prepare will have some checksum, and it will point to the previous prepare. And that in turn will point to the previous prepare. So again, let's say that like this one here, checksum 92. Then here, parent will be like, let's say 62, and well, checksum of this one, let's see, will be 62, but the parent will be 92. And then for the next prepare, again, parent will be like 62, and the checksum would be like whatever is the checksum for the current prepare. Those checksums are cryptographic. So there's like 128 bits there, and that means that probability that two checksums coincide by accident is negligible. Even if you take into account things like WD paramex, like there is enough entropy in 128 bits to basically assume that no collision could happen. Because of this, it actually is true that the checksum of a single prepare completely pins down the entire history. because this checksum over here, covers this parent, which is this checksum, which covers this parent, which is that checksum, and idem. Well, not idem literally, but up to like the original root prepare, which is just hard coded. So let's get back to our also white label document, which we haven't touched in a little while because we're preparing for like diving deep into pragmatics here. So we have event source, which means that the logical model is the sequence of events. And it is implemented by replicated state machine. Because, well, we want to do event sourcing, and we want reliability, or actually, yeah, we want to have availability, so we must distribute the state machine. And we also need performance. That's why we add snapshots, and that's where kind of like just logical event sourcing turns into physical replicated state machine, at least in my mind. Okay. Then we have hash chaining, which is just like you don't need hash chaining to implement a replicated state machine, but if you have it, it improves, well, first of all, it improves safety because you get like whenever you have like two events in your log and they're neighboring to each other, you could actually check that parent links are correct. You don't need to kind of like just assume that, hey, due to, for example, sequence numbers being different, those things follow each other. You have like very direct cryptographic proof that, hey, those events are indeed in sequence. And this in turn allows you to detect any violation there and fail early. So hash chaining is important for safety, but it also is quite important for efficiency. Why? Well, because with hash chaining, you don't need to transfer the entire state of your system at the same time. You could just transfer 128 bits of the root hash and say, hey, this root hash is what the current state is. And because everything else then changes to this hash, you can effectively restore the state of the system piecemeal. So kind of like, yeah, hash chaining is one of small mechanisms which makes pragmatics of consensus easier. Okay, so that was hash chaining. Now let's look more at the mathematical side of things. So okay, we have like this nice sequence of events which we're like slowly trying to build up from. And because this is consensus, this is probably done by a certain like primary state machine. So this is a primary. It has its little crown as a primary, and this chain exists inside of the primary. But we know that the problem with the primary is that the primary dies, and then the primary, who usually dictates what gets into this chain of prepares, cannot make any decisions. So a different primary should be able to take over. And it might even be the case that the sequence of events on a different primary will be slightly different. So again, let's say that this primary decides that, hey, the red should really be continuation here. And before this red gets out of the primary to the rest of the cluster, or maybe it like only gets like another, only one another replica, and then kind of like all the replicas which had any information about this red one died. So when we get to this new primary, it kind of like, okay, it has the same sequence of like those three events, but here it actually goes and okay, I'm out of color. So yeah, let's say that's another green. And this like new primary just goes and says, hey, actually, I don't know anything about that one, and I need to continue the chain somehow, and I'm going to like accept this new green prepared here. And like this is all. This is something which inevitably happens. This is something which inevitably happens in your consensus algorithm. You cannot like for any specific decision you're trying to make, you can't be sure that this decision survives. Like only after you have enough of confirmations from other replicas, you might be sure that this decision is durable, but after that, the decision can always be reversed. So the picture you should have in mind here is that you have a sequence of events, and for some events you are like pretty sure that hey, this is actually the true state, and whatever primary is going to be in the future, this primary will be sure that those three events persist. But for the very end of your chain, like for the last event, you might actually not be sure. You might be, hey, kind of like maybe this event is going to become committed. Maybe it is part of the state, but you are not sure. There's always like, this probability that actually that like this one isn't actually true, and the true one will be like the blue one here. So okay, how this is modeled in our consensus algorithm. Sorry, I get too excited here. How is this modeled in our consensus algorithm in code? So, first of all, okay, let's discard this. First of all, each replica maintains a log, and the last entry of this log, what is like the tip of a branch. I guess I have a tendency to zoom out really far, and then nothing is visible. That's a shame. Okay. Let me make this smaller so that we can zoom back to a reasonable size. So that's okay. I need to make a little smaller still. Okay, perfection. Now we can say that this is actually up. Okay, yeah. And let's say that's like up points to this last prepare in a replica's local chain, and you see here that yeah, that's like this is the number of the latest prepare that replica has. And then replica nodes which prepares are durable, which prepares are committed, which prepares are guaranteed to survive into the future arbitrary. And for those, we have commit name. Then another crucial parameter, another crucial bit of state that replica has is the view number. So view is roughly the same thing as the round or ballad from the last lecture. So the view decides who is the primary, who the replica listens to, and views only increase. So there is like a sequence of views. Each view has a primary, and a primary for a view is determined primary index, like in the most simplest possible way. Basically, it's just the number of replicas. Well, it's just like the view number, which is an integer, modulo number of replicas. So, okay, a replica has a view has a primary. And the invariant the replica maintains is that when it is in a particular view, it will never ever respond to any messages from the previous view. So yeah, if replica decides that, hey, I'm going to be a part of a view 12, it means it will never participate anymore in views like 2, 3, 4, up to 11. So only in the view number 12 right now, and maybe in the future, the replica might decide that, hey, actually, I don't like view 12 anymore. I'm going to switch to view 15. But if it does that, then, well, it can no longer participate in view number 12. Okay, so and that's kind of like basically the core idea of bootstrap replication. We slice like our history in views. Inside a single view, there is a single primary, and a single primary builds this chain of events. So to build an event, primary broadcasts it to peers, and peers reply with acknowledgement messages with prepare rocks, and kind of like once primary accepts a quorum of prepare rocks, it actually says, hey, this message is now committed because it is replicated to a sufficient number of backups. But as usual with consensus, we always keep in mind this possibility for primary to go offline, for view to end. And that's why there is also a part called view change protocol, which describes how a primary in a future view can take over the history of a cluster. And okay, now imagine like you're like a replica and you are a backup in a view number 12. And it looks like view number 12 is stuck. Like you haven't heard from primary for like 5 minutes. Like probably primary is dead. And like the next view is 13, and you actually are a primary in the view 14. So you're thinking to yourself, hey, actually, it looks like the view I'm currently in is kind of like broken. It seems like the primary is dead. And I probably should move on to the next view, and I should probably become primary. Well, and like in the next view, I am becoming primary. So what should I do? Well, the first thing you do is that, well, you decide, hey, that it actually makes sense to start a new view because, well, maybe it's not actually the primary of the current view who is dead. Maybe it is you who is partitioned from the cluster. There's kind of there's like some protocol which we need to employ to decide that hey, it's a good time to switch views. But assume that we figured out that it's probably really the primary is dead. What we do then? Well, using your primary, you want to do two things. First of all, you want to collect all the history in the cluster up to this point to make sure that you have a complete log, to make sure that you haven't missed any prepares from previous views which were actually committed. Because if prepare is committed in one view and then stops being committed in the next view, that's like safety violation. The second thing you need to do is that you need to ensure that no previous view can progress. So you want to actively block all previous views from progress. And that is where we get that same mechanism, which we were discussing last year, where you, as a primary, collect a quorum of backups, make them promise to never ever participate in previous views by forcing them to increment their view numbers. Then you ask those primaries about all the prepares they know about. And that way, you learn the most complete picture of a cluster that there could be. Because, well, okay, that's actually wrong. You don't necessarily learn the most complete picture of the cluster. Because, for example, let's say you have 6 replicas, and in the previous view, primary get repair and duplicated it to a different backup. And then those 2 replicas, the primary and the backup got prepare, they kind of like disintegrated. So like the knowledge in the cluster is okay, there's actually that new prepare which wasn't yet committed. And using primary, you wouldn't know because well, it was only replicated to 2 machines and you don't have any access to those 2 machines anymore because they're gone. But what you will have is that you will have knowledge of any prepare which could have been committed because there is a quorum condition. You replicate prepares to a certain amount of machines, and then when you become a primary, you also require a quorum of a certain number of machines. And because those quorums are big enough, they are guaranteed to intersect. So if a prepare was committed in a previous view, then at least one machine will participate in your view change. And that's why you will learn about this prepare. So, okay. Let's roughly look at that in the code. Again, I think I will probably be spending more than 1 hour. Well, not 1 hour. Well, I will spend 1 hour today, but overall, over like maybe 2, probably even 3 episodes will be like talking kinds of because there's like a lot of details to cover, and I'm going to kind of like basically slowly build a picture, like starting in the middle of things. Okay, so we looked at this primary index, which dictates which replica is the primary in the current view. Then, if we look at our messages, we see that besides prepare, we also have start view change message, which is a part of that protocol where we decide that it might be a good idea to start a view change. And then we have do view change. This is part of the protocol where a quorum of replicas decides to actually switch to a new view and kind of like build a union of all their local prepares to complete a picture of all committed prepares in the next view. And then in replica, we also have this curious function view jump view here, I think. Jump to the jumps in target. Oh, it should be okay, it is here. I'm wondering why why it is not. Okay, now this is not. Maybe I'm using better techniques. Anyway, we have like this jump function, which causes the replica to durably commit to not participate in any earlier view. So basically, if a replica receives a message and it turns out that uh, the view in this message is actually bigger than the current view of the replica, then the replica is going to somewhere it's going to adjust its view. Okay, where do we set view? Yeah. Well, actually, okay. That's interesting. I think. What? We should be incremental view here. I think. Oh, yeah, right. So if replica learns about the view, it's going to transition. Yeah, it's going to transition to a new view, and once replica in a new view, it starts ignoring all messages from the previous view. So you could see, like in a lot of like this ignore message kind methods, we just say, hey, precisely like refuse to participate in all reviews. Okay, so that is, I guess, roughly the structure of consensus. Now, what are some interesting applications here? Well, kind of like if you like naively think about how you would implement this, it will look something like this. So you're a primary, you receive a prepare, then you replicate that prepare to a bunch of backups. Then you receive acknowledgements from the backups that prepare is there. And acknowledgements are, actually, let me show you these acknowledgement messages. Acknowledgements are called prepare case. So you primary, you replicate prepare, you collect a quorum of prepare case, and that means that the message now is guaranteed, the prepare is now guaranteed to survive in any future view. So you could consider it committed. So you adjust local commit mean, and actually that's going to be commit packs, because that's what's the cluster committed. We'll talk about commit mean relatively soon. And then you kind of like adjust to the next prepare. So kind of like let's simulate this. Okay, let's say that we are primary. This is kind of like our idle state. We don't have any prepares on top of it. Then we accept a new request from client. We append a new prepare on top of our hash chain. Again, this all hash chains. So this is important. Again, this thing hash chains. And like this happens inside like the primary. Like then you go and you let me kill this thing because it does not really need it anymore. Let's say those kind of like, say like this is you, you're like the primary, you're big important, and you have this little crown, and then there is a bunch of backups. So After you as a primary accepted this prepare, you're going to, and let's say for simplicity, let's say there's like only 3 objects, so the quorum is like 2. You go and replicate this prepare to 2 of our backups. And then backups go and okay, I guess I need to curve here. Go and reply back to you with prepare OK messages. So this one here is prepare. And this one here is prepare OK. So this one replies, and this one replies as well. So what you end up with is you end up with a quorum of prepare OKs. So there are like 3 topics in the cluster. You got 2 prepare OKs. That means okay, that's a quorum you could advance. Well, actually, before okay, the very first thing you do once you get this prepared, actually, move forward your op, because well, you kind of like want to capture, okay, there's like this one extra new message which is in the process of being prepared. So okay, now that you collected the quorum of case, you could actually color this message as, hey, this is logically committed. You move your commit pointer to point to this message, and here you actually execute the operation, which means, again, something we looked at before, which means that we execute prefetch operation in the state machine, which goes to disk and reads all the data that we need to execute this operation, and then execute commit, which actually does all the necessary CPU work to figure out which transfers pass and which transfers should fail. Okay. After you've done all that, you could just go and move on to the next message, to the next prepare. And that's native implementation. And the problem here is that it is like there is not enough pipeline. If you recall back then when we were discussing why Pragmatics is single-threaded, there was like 2 ideas. One idea was that for financial transactions domain, there is very fundamental bottleneck in the logical model itself, where you really need to synchronize everything. So like the amount of data parallelism you can extract from your data is small. That's why the thing is single-threaded, and that's why we try to pipeline everything. That's why we like, if we have like 5 batches of transactions in the network, we like, although like we want the actual business logic to execute strictly sequentially across all 5 of them, we want to overlap any other auxiliary processing as much as possible. And in particular, when we execute a single prepare, we want to, in parallel, fetch all available data from disk. So here, you see that we kind of like miss, wait a second, let me turn up the lights here because it's getting dark. Okay, I'm back. And hopefully now I will be able to see everything better. Yeah, you see, there is an opportunity for pipeline here. There is like latent concurrency, which is not exploited here. Because if you think about what happens, well, we receive a request, we convert it into prepare, then we distribute prepare over backups, and then when we receive prepare case, we go and execute things. And while we are like, when we are waiting for prepare, so that's basically when we are waiting for prepare case, that's basically like network delay. And then when we are executing stuff, that's basically like our CPU bound. And like our input output and CPU usage happen one after another. So there is no pipelining. We kind of like wait for both network and CPU. And it'd be cool to kind of like somehow make things a little less rigid. And in terms of like they a little less rigid in terms of the specific sequence we run the processing in. So what actually happens is that okay, let me kill most of things here. So what actually happens in our consistent algorithm is that the primary has a whole pipeline of uncommitted prepares. So if 3 requests arrive at the primary, it just going to optimistically arrive at some sequence for those requests, create 3 prepares, and then actually let me use different colors for them. And then start in parallel distributing all those prepares across different replicas. And let's say, for example, this one gets green, and this one gets red, and this one also gets red, and this one gets blue. That means that kind of like we get commitments out of order. So for this prepare over here, we kind of like say, yes, that one collected form. But this one here, for example, didn't collect the quorum, or it like might actually be the case that they both collected quorums, but for like using different subsets of replicas. Well, okay, let's say that this one is also replicated to here. Okay, so that means that the primary can wait in parallel for input output for many prepares. And as soon as, so okay, and the op will be pointed to the latest one here, yeah. So, and kind of like, as soon as we commit the next prepare, then we are going to adjust commit, and then we're going to run execution. But everything on top of us in the pipeline can do input output in parallel. And that's actually cool because, well, if you think about it, like kind of like CPU is probably not a bottleneck. Probably what is like slow is actually writing data to disk and transferring the data across the network. Well, it's not, again, disks are fast, networks are also pretty fast. It turns out that that's like not necessarily like slower than the CPU, but well, it might be slower, but it's definitely more variable than the CPU. Like that's where kind of like sometimes it takes like 1 millisecond, and sometimes it takes 10 milliseconds. So by like aggressively pipelining in the future, you are able to average out over all those latencies and kind of like hide any slower state. So let's actually document this in our white terminal. This idea is prepare pipeline, and that goes back to embracing fancy, basically. Because, yeah, why not? If you could concurrently schedule several prepares to like go through replication mechanism, why not? Okay, so that covers kind of like parts of our pipeline. Let's maybe change gears from like, my horrible drawings and actually look at the code, how that all works out. So again, let's trace a path of the request, but let's pay closer attention to this pipelining aspect. So a new prepare appears as a result of a request. So we go to the onRequest method of the replica. And we see that if we are not a primary, we're just going to ignore request. And like, you see how it's great that we like have this extra assertions, because not only they enforce correctness, but they actually make the code much more readable. Because if you see this assert self-primary here, you can be sure that the logic in ignore request actually ignores request for all non-primaries. Okay. So if we are primary, we get a request. What do we need to do? Well, first of all, it might be the case that our pipeline is full because, again, everything has a limit, and in Pragmatics, we are not going to pipeline indefinitely in Pragmatics. So we have only pipeline prepare Q max outstanding prepares. And going back and back and back, yeah. So if the pipeline is full, we are just going to queue this request. Again, when a request gets into prepare pipeline, that means that we assign a particular sequence number to these requests relative to all the other requests. If actually, okay, actually, I think I might be lying to you. So I think, well, so basically what happens here is that we have like this prepare pipeline, which is a number of concurrent prepares which exist in the cluster and basically flow between replicas. But also primary has this queue of requests. And requests are, well, requests which don't fit into pipeline for prepares. So they're just queued up without being converted into prepares. And I guess the difference here is that, as we will see, the size of our pipeline defines the consensus algorithm. So basically, when we do a view change and a new primary needs to collect all the data, it needs to think about a pipeline worth of outstanding pull requests of outstanding prepares. While the request queue is local to a primary. So, and the different primaries might even have like different request queues added like that. Anyway, so let's go to the set case. We have a request, pipeline queue is full. So we try to queue up a request, and somehow we are able to always push a request. And I guess that means that we, in ignore request message, we actually check that we have enough space here. Should be hand. Well, okay, yeah. I'm not seeing this. Okay, yeah. So what I'm puzzled at, like we want to accept request. Obviously, like because everything is limited, we cannot always just put request in. So there should be some logic which says, hey, actually, let's drop this request on the floor. And I'm not quite seeing it here, but it should be here. Okay. Maybe ignore request now. Those should be. No, there we check for backups. And here we check if we might already be preparing this message. Okay, this, I think. Okay, yeah. This is what I was. This is what I was wondering about. So this full method returns true if both the pipeline queue and request queues are full. So I guess on request, we could also say that pipeline queue full, not cache queue. That's like when you miss assertions, is actually might when you miss assertions, it might actually become harder to see what's going on here. Anyway, so like confusing bit here is that notice that we have queue, and this queue inside has two queues. There is there's prepare queue and a request queue. So we assert that the queue isn't full, and that means that either prepare queue is not full or request queue is not full. So if a prepare queue is full, we just queue up a request. If both of those are full, we just ignore the request completely, and the client will just present it later, no problem. And the happy case is, well, we want to pipeline this prepare. So okay, we have our request, and then we convert this request into a prepare. And the core thing we are doing here, like what does it mean to convert a request into prepare? It means that we assign the iteration number. So when client sends us a request, it doesn't know the order of this request relative to all other concurrent requests. But our linearizability guarantees require us to actually, well, pick the order among all concurrent requests. And that's exactly the job of the primary. Kind of like this single line here is basically like the whole shebang. Like, why do we do this? That's like where magic happens, that's where we assign a sequence number and make things happen in a particular order observable from the outside. Okay, so we get this message. And then we add this message to the pipeline queue. And I think at some point we should be we are transmitting this prepare. Let me find this code here. Interesting. I'm not saying this because yeah, kind of like what I want to show is like when we retry setting the prepared, because here on prepare uh, we try to replicate this message only once, and obviously that can fail. So there should be some code to on the timer try to send prepares for those prepares which are stuck in the pipeline, which don't receive enough prepare keys. Okay, that's normal replication. Okay, let's see that. That should happen on timer. So we must look at what timers do we have. That's okay. So here are always okay. You see, all the timers are through these timeout structs. So you could look at all those timeouts and see all the like periodic things that replicas do. And here we have this prepare timeout, and that presumably handles rebroadcasting of prepares from a pipeline. Let's see here. Yeah, I think that's I think that's it. So if this timeout fires, then we pick the first prepare, which haven't yet received a quorum of prepare OK messages, and then we should try. Okay, well, where are we finding the one to? Yeah, let's see. Let's find replica whom we need to send this to. So this is all replicas. Then we okay, that's just confusing. It says that all from all replicas iterator, but it actually like it's actually not okay. That's like very much not okay because we are looking for replicas which haven't sent us prepare a case, and we add them to this list of replicas which uh, which we should try to send a message to. Okay, and then we just pick next replica in this list, and we send a message to this replica, and this kind of sounds a little bit fishy to me because that means that we kind of like deterministically pick a specific replica, and kind of like my gut feeling says that probably it's better to pick one at random. But oh, anyway, I guess that doesn't feel right now. What matters is that yeah, while we have this prepare in a pipeline and the prepare haven't collected enough prepare case, we are just going to retransmit this prepare to backups. And then hopefully we receive a prepare OK from another replicas. So let's now look at the prepare OK path. When we actually make up our mind that, hey, a particular prepare gets in, it wins. Okay, so we receive the prepare OK, and we check if this was the prepare OK, which actually triggered that transition, which completed the quorum. While that happens, we say commit pipeline. We say that some messages in our pipeline can be committed. And here, I think we should find out and prepare that we want to commit. Okay, commit dispatch, next pipeline. Let's look what we do. Commit next pipeline. Okay, we pick prepare, and if it have received form, again, kind of like if the next prepare doesn't have a quorum prepare case, we cannot commit it, obviously. In that code path on prepare OK, we actually specifically checked that, hey, there is a quorum here, but I think this commit pipeline is just running in a loop. So we just checked that, hey, the first one have a quorum, but the second one might or might not have it. So we can just, try running it again. So, okay, if we have a quorum, then we run through this commit. I think, I want to find out where we adjust our commit paths, because I think it should probably happen here. Let's just find it this way. Commit journal. Yeah, so we run pipeline confession, then we get into the commit op, which actually runs the state machine state machine commit operation, which like does the actual processing. And then here we adjust our commit max. And I realized that I somehow told you about pipeline, but I haven't told you about commit min, which is very surprising because those two are like pretty significantly interrelated. But I guess that's going to wait until next episode. So let's leave it at it. Let's leave it in the midst of things and see you next week. But before that, a short recap. So today's we started discussing pragmatics of our consensus algorithm. The first thing we've discussed is that instead of building consensus for a single event, a single outcome, we are actually going to decide on a sequence of events. The second idea was that of hash chain. To make our lives easier in all the various places, we are just going to hash chain that sequence of events, which gives us pretty strong guarantees that we cannot accidentally flip the two events with each other, because, well, it's like a mass hash chain, and like you cannot accidentally break hashes, which is good. And the final thing which we've started looking into, but haven't completed yet, is that this idea of a pipeline. That when a primary wants to append a message to the log, it doesn't necessarily need to append all the messages one by one. While the actual execution of the operation must happen sequentially, the primary can actually go and optimistically start broadcasting a pipelining of prepares across backups, hoping that we all get committed. So we prepare messages out of order while we commit in order. And because commit is actually CPU bound and this is just like synchronous execution of this operation, that means that we are able to pipeline the hard stuff. We are able to pipeline in input output and disk I/O. And more about that next week. Thank you for joining Iron Middle today, the first episode of 2024, and hopefully this time we'll get really a year full of episodes. I'm wondering when we will stop covering existing code and start looking into new developments, but well, hard to predict the future. We'll see, and let's not try to pipeline this too far away. Okay, thank you, and see you later.